Recursion is a concept that baffles countless programming beginners, yet it serves as the foundation for many advanced algorithms. The essence of recursion is actually quite simple. It is about a function calling itself. For example, once upon a time, there was a mountain, there was a temple. In the temple, an old monk was telling a story. What story? Once upon a time, there was a mountain. On the mountain, there was a temple. In the temple, an old monk was telling a story. What story? Once upon a time, there was a mountain. If we were to code this, it might look like this, within the definition of the foretell story function. We call the foretell story function again. After calling it, you would see output like this. Another example, when you search for recursion on Google, the results page will ask, "Did you mean recursion?" Clicking on recursion takes you back to the same results page, which again asks, "Did you mean recursion?" It's like a digital ghost haunting you. However, the real purpose of recursion is definitely not to make your program loop endlessly, but to help you solve complex problems. Specifically, recursion can break down a large problem into smaller problems of the same type until they become small enough to be solved directly, thereby solving the original large problem layer by layer. For instance, imagine you are in a very, very long queue and want to know your position. The solution is simple. If you can find out the position of the person in front of you, just add one to get your own position. But the queue is long, and the person in front of you doesn't know their position either. However, they can ask the person in front of them. This continues, one asking another, until the person at the front of the queue turns around and says, "I am the first." Then the person behind them can know their position and turn to tell the person behind them, "I am the second." Next, the person behind them can know and turn to tell the person behind them, "I am the third," and so on, until the person in front of you turns around and tells you their position. Then you can calculate your own position by adding one to theirs. Therefore, recursion requires a termination condition. When this condition is met, the function stops calling itself recursively. In this example, the termination condition is when the person at the front of the queue turns around and says, "I am the first," instead of continuing to ask the person in front. If your recursive function lacks a termination condition or never reaches it, it will lead to infinite recursive calls until the program crashes. For example, function 1 has no termination condition, while function 2 uses saynum == 0 as the termination condition. However, if we pass it a positive number, the function internally calls itself with the parameter incremented by 1, never reaching the saynum == 0 condition. Why does infinite recursion cause the program to crash? Because each function call adds a new stack frame in memory to store the function's internal state, such as the values of local variables, as each function call operates independently. However, stack space is limited. If we keep calling functions without returning, once the stack is full, a stack overflow occurs, causing the program to terminate abruptly. The well-known programmer Q&A community Stack Overflow. Understanding recursion doesn't mean you can write recursive functions easily. Writing your own recursion is a different challenge altogether. Suppose we want to write a function to calculate the factorial of any natural number. The factorial of a positive integer is the product of all positive integers, less than or equal to that number. For example, the factorial of 3 is 3, 2 times 1 equals 6. Additionally, by convention, the factorial of 0 is defined as 1. Here, I'll teach you a 3-step method to write a recursive program from scratch. Step 1. Define the function's purpose. We can define a function called factorial. Its purpose is to take any natural number as an argument and return the factorial of that number. For example, calling factorial 5 should return 120, which is the result of 5 sewing 4, 4, 3, 3, 2, 2, Darwin 4, 1. Step 2. Identify the base case. The base case determines the termination condition for recursion. Think of the base case as the smallest version of the problem that can be solved directly without further decomposition. At this point, the function stops calling itself and returns a result directly. Based on the earlier definition, we know directly that the factorial of 0 is 1. We can include this as part of the termination condition. We also know that the factorial of 1 is 1. So we can add this as a termination condition as well. Step 3. Define the recursive case. A recursive function generally consists of two key parts, the base case and the recursive case. We've already defined the base case. The recursive case is what happens when the base case isn't met. The function calls itself to solve a smaller instance of the same problem. The key here is to find the equivalent relationship after decomposition. For example, the factorial of 100 can be broken down into 100 multiplied by the factorial of 99. The factorial of 5 can be broken down into 5 multiplied by the factorial of 4. The factorial of 2 can be broken down into 2 multiplied by the factorial of 1. In other words, when Cunman is greater than 1, calculating the factorial of Senbang can be decomposed into calculating Fundang multiplied by the factorial of Tunman 1. Thus, the recursive case can be written like this. The crucial point in finding the equivalent relationship is to assume that the recursive call will give us the correct answer. In other words, while writing it, you must believe that 10 factorial. One will correctly compute the factorial of Thiding 1. Then, the factorial of 5D inclusive n multiplied by y factorial 1, which is logically sound. If the base case is correctly defined, the decomposition relationship is accurate, and each recursive call moves closer to the termination condition. Trust me, the recursion will work correctly. If you prefer, you can simplify the termination condition to just tonight equals 0, because even if nd full equals 1 is handled in the recursive case, the result will still be 1. So far, the recursive function for calculating factorials is complete. Now, let's see how recursive calls are executed. The execution of a recursive function occurs in two phases, the winding phase, going deeper, and the unwinding phase, returning back. During the winding phase, the function calls itself layer by layer until the termination condition is met. Then, in the unwinding phase, it starts returning from the deepest layer, where recursion terminated, back up, executing any remaining code in each layer as it returns. For example, let's revisit the Halder factorial function. The program starts executing from the full_min function, where we call the fulna factorial function, passing the integer fulnum with a value of 5. The full_that factorial function begins execution. N equals 5, which does not satisfy the base case, n equals 0, so it executes 5n n asterisk factorial 1. This marks the start of the winding phase. It needs to compute factorial 4, adding a new stack frame to the call stack. N equals 4, which does not satisfy n equals 0, so it needs to compute factorial 3, adding another stack frame, n equals 3, which does not satisfy n equals 0, so it needs to compute factorial 2, adding another stack frame, n equals 2, which does not satisfy n equals 0, so it needs to compute factorial 1, adding another stack frame, n equals 1, which does not satisfy n equals 0, so it needs to compute factorial 0, adding another stack frame, n equals 0. The termination condition is met, and the winding phase stops. Now the unwinding phase begins, returning results, layer by layer. Factorial 0 returns once, and its stack frame is popped from the stack, freeing the memory. Factorial 1 receives the result 1 from subfactorial 0, returns 1, and its stack frame is popped. Factorial 2 receives the result 1 from subfactorial 1, returns 2, and its stack frame is popped. Factorial 3 receives the result 2 from factorial 2, returns 6, and its stack frame is popped. Factorial 4 receives the result 6 from factorial 3, returns 24, and its stack frame is popped. Factorial 5 receives the result 24 from factorial 4, returns 120, and the program returns to the point in Fuiman, where factorial was called. Then, it continues executing the remaining code in Fuimeimei, assigning the value 120 returned by factorial to the variable result2, and finally printing the result using Fuiprint. Once a main print finishes executing, the entire program ends. Have you learned it now?